In our previous per unit method videos, we discussed more theoretical and potentially difficult to understand concepts regarding the per unit method. And with this third video, we're actually entering into a somewhat easier phase. We're going to be not so much on the theoretical side and more on the formulaic side. What this video is going to be dedicated to are the base formulas. And what I mean by that is the formulas we're talking about are the ones used to establish the bases. That is, the bases you didn't pick to begin with. Now, if you recall in our previous video, we said that you're supposed to pick two bases and derive the other two bases as a part of the per unit method. So we're talking about the formulas used to quote-unquote derive the other two. That's the area that we're analyzing in this video. It's really important for you to understand how simple these formulas are because they really come from the two most basic electrical engineering formulas that we deal with as PE studiers. That is, the P equals VI formula and the V equals IR, or IZ if we're talking about impedance as opposed to resistance. Anyways, what could be more fundamental than these two formulas? And these are really going to be the formulas that are going to pervade all areas of our discussion with these base formulas. We can divide the discussion of base formulas up into two broad sections. One is the base formulas for single phase, and the other would be base formulas for three-phase systems. We are going to begin our discussion showing the single-phase base formulas. Our first formula will be our base current formula, and that's very simple. It's current equals base kVA over base voltage in kV. Now, what I mean by that is we have really a simple application of the P equals VI formula to derive current. Now, we had said in our previous video that usually power and voltage are the given bases. They're the ones that you pick or that have been picked for you, and you're left to derive current and impedance after that. So that's sort of the idea behind the way this formula is written here. If you have your power and your voltage as a given, you're using those to derive your base current. Now, this formula can be rearranged very conveniently if for some strange reason you were given the base in current and you needed to find your power base or your voltage base. We can see that using the P equals VI formula in this way can be used to determine current or power or voltage. Now that we've derived our current base from the chosen power base and voltage base, we would move to the fourth base in our per unit method, which is impedance. And so you can see sort of chronologically with a derived current base, we can use the chosen voltage base to come up with our current base. A very simple application of the V equals IZ formula at the top there. Or if you chose not to use the current base to derive your impedance base, you can still actually use a power and a voltage base to come up with that. And instead of using just the V equals IZ formula, you would use sort of a combination of those two very simple formulas to come up with this third overall formula at the bottom here. This third formula of impedance equals voltage squared over power should be sort of in your bag of tricks of formulas, if you will. It's another very simple formula. And we'll just go through the algebraic spelling out of this formula to demonstrate its roots in our two very fundamental formulas at the top. You can very obviously see that what we've done here is we've taken the two standard equations and rearranged them algebraically to solve for current. Since both of these solve for current, we can combine them algebraically now and use the combination to solve for resistance or impedance. And obviously R can be Z, so we see in this final derivation here that we have the same formula in essence of this other base derivation formula here. So we can see with just these three formulas, we can derive any of our four bases based upon, obviously, which two were selected in any single-phase problem that would require the per unit method. Now let's write the three-phase formulas that you will need for the bases. You'll notice that the three-phase formulas there are only two as opposed to the three formulas for the single-phase section. So we're knocking one of those off, and that should be helpful because the three-phase is maybe a little harder to understand. So where we gain difficulty in its understanding, we also gain simplicity in the number of formulas we have to recall for it. And speaking of gaining simplicities for the formulas needed to be remembered, you'll notice that the impedance formula that's being written right here is actually going to be the exact same formula that we see for the single phase. If you notice our B subscripts, we're just going to, instead of writing base in the subscript, we're just going to shorthand that using B. Now, we are not completely done in our understanding of these formulas, because these two formulas require a certain set of conditions in order to be used correctly. So when we ask ourselves what could these conditions possibly be as we look at them here, we should let our eye wander back to our first formula under the three-phase flag and look at that denominator and see the root 3 in play there. What does that make you think of? When you look at this root 3, it should sort of make you think of something pretty obvious to all of us, which is the distinction between line and phase values. Well, when you go over to the conditions we've set out and you look at our voltage base established there, you will see that the voltage base is equal to the line voltage, but it's also equal to the square root of 3 times our phase voltage, which is really just a conversion of phase voltage to line voltage. So you can see in the consideration of our three-phase base conversion formulas, we have to build in a consideration of, are we dealing with line values or phase values? So these two three-phase base formulas require you to use line values and total values. Once you have your choice of voltage, you're going to use this formula, you need to make sure that your voltage choice is line voltage. If you have selected phase voltage and still want to use this formula, then you need to run the square root of 3 to get to line voltage, which is your base voltage. The same is true for power. If you're going to use phase power, you need to convert that over to total power. So these two formulas, very simple, very easy to remember, but you need to understand that these do not work in every single case. They only work with the understanding that you are using line and total values as your chosen bases. And there is no such restriction on the single phase side. So notice there is a difference. We're sort of having a paradigm shift from the single phase formulas over to the three-phase formulas. Now we have several videos in our square root of 3 section that you should refer to if you don't understand what's occurring with this phase to line conversion. It's important that you understand the square root of 3 video content in order to get what we're saying here. If we take just a step back now and look at these two three-phase formulas, we need to just realize very simply that we are putting in line and total values. That's how these formulas are doing their work. So we put them in to these base formulas, and then what we're getting out are per phase base values. So our actuals are line and total. If those go in, base formula does its work, and what it spits out are per phase base value. Now it's pretty incredible if you think about it that we have a set of formulas where you input a line and a total value, and then you get out a per phase value. You really should sort of sit back and ask yourselves, why is that happening? What about the per unit method is being accomplished here? Why do we need to move from line and total to per phase values? Well, in balanced three-phase circuit analysis, what we actually end up doing is treating it like it is 3 individual single-phase circuits. So what you have actually in your circuit analysis is, in a sense, per phase voltage and 1/3 of the power being demonstrated. But you have it demonstrated 3 times essentially. So this means that 3-phase circuits are solved as 3 single-phase circuits. Now let's take a look how this inputting of line and total values, yields per phase values, and the discussion of the three-phase circuit analysis as it applies to our three-phase base formula here. So first, let's establish our per phase power here, which equals the total power over 3. Because remember, we're dividing our total power by 3 into 3 individual single-phase circuits, and our phase voltage is our line voltage over root 3. And remember, we're solving for current with this formula, so we're going to use our simple P equals VI algebra and demonstrate that here. Now moving to our desired outputs, we are going to add in our phase subscripts to demonstrate that we will be getting phase values out. So you can see our desired output of phase current is demonstrated here as our total power divided by 3, which is our phase per phase power, over our line voltage divided by root 3, which is our phase voltage. So our phase current is a division of our power per phase over our phase voltage. Now all we have to do is a little bit of algebra to see how our root 3 gets finally rearranged in all of this. So notice we end up with this formula right here, which just so happens, well, it doesn't happen to, it actually does correspond with this formula. So now you can see sort of the logic behind why this formula is used for three-phase base formulas. Now in our next video, we are going to wrap up our discussion of base formulas and talk about our base conversion formulas for the